we'll wait for other 5 minutes. Let others to be joined. Yeah, Usma madam, you can start the session. You can introduce the resource person and start the session.
Thank you, sir. Good evening, all. Good evening, madam. Welcome you all to another session of Faculty Development Program on emerging trends in VLSI design for signal processing and communication systems. We are honored to introduce V. Rajita Rani, DFT engineer at DFT Semiconductors Private Limited. She holds her master degree in VLSI design and is presently pursuing PhD in the area of design for testability from Jawaharlal Nehru University, Hyderabad. She brings with her a rich blend of 15 years of experience, comprising 12 years in academics at various reputed engineering colleges and 3 years in semiconductor industry in specializing design for testability techniques. Her core expertise includes digital VLSI design, testing methodologies, fault modeling, scan design, and built-in self-test. Her industrial role emphasizes applying DFT concepts to real-world semiconductor design challenges. With her ongoing doctoral research and professional engagement in DFT, she continues to contribute significantly in bridging gap between industry and academia. It is our privilege to have V. Rajita Madam with us today to share her valuable knowledge and insights. I request you, Madam, to please start the session.
Thank you, Hasna, for the introduction. Yeah, am I audible? Yeah, thank you. Yeah, let me share my screen. Is my screen visible?
Yes, madam.
Yeah, okay. Yeah, as we know, today our topic is contemporary advances and research directions in VLSI design and technology. As we know, there are several fields in VLSI. Actually, we can go with the many fields in the sub-contemporary areas of VLSI. And these are the different stages in VLSI, where we can decide the specifications. Actually, anyone can decide the specifications, as we know. But the thing is, what is the importance of this architectural design engineer is when you decide the specifications, we should think of whether that particular design is possible or not. Where that architectural designer importance comes into picture actually. See if I give nowadays the ongoing technology is gigahertz technology, like a 4 or 5 gigahertz technology is going on. Like if I give a design where it should reach 10 gigahertz, means it is for today's technology it is impossible to reach that. So that ideologically we should reach the specifications. Like that we should decide our specifications actually. Okay, that's where the architectural design engineer comes into picture. Actually, this the person who decides the specifications and all, when that person knows all these stages, only that person only can decide the range of CEOs and all. Actually, top level engineer we can say. And then based on the specifications, whatever is decided, then RTL designer comes into picture. As we know, like a Verilog, VHDL, generally used languages. Nowadays we have system Verilog and UVM also for the implementation. that designer, depending on the specifications decided by this architectural engineer, he will develop depending on the real-time structures, like what are the kind of tools we are using, what are the kind of real-time environment we have, what are the applications, and what is the accuracy we need. Based on all those specifications and inputs, the RTL designer will develop and synthesize that model. And when we talk about these two stages, actually, when we talk about specification and architectural design engineer and RTL design engineer, actually in these two stages also, generally there will be multiple engineers involved, sir, like around 10 stages, I can say, who decides architectures, like if temperature, if it is related to temperature, one engineer will decide what are the possible temperatures. If it is power, what are the possible powers it can reach, what is the like a minimum power consumption it can take. Like that, depending on certain important features, each engineer will involve actually when it comes to real-time development. Like broaderly, when we discuss, this architecture designer might look like a single engineer, but there will be multiple engineers involved in it. In this RTL design and synthesis also, like design will be done by.
Madam, sorry for interruption. Can you use the presentation mode, madam?
Yeah.
Bottom.
Yeah, this one. Yeah, just a minute. It is F5 only, right? Sorry.
Yeah, otherwise, rightmost corner, so you have the size is there. Can see,
Right.
the
Where
bottom.
can I actually?
Right bottom, right side bottom. So fourth one. So no, not that
It's
one. So after this, next. Yes,
okay.
Yes.
Yeah, okay. Thank you. Actually, F5 is not working, so I'm continuing with that.
Okay, no problem, madam. So you can use hide also this one. You can hide this. Stop sharing is there. No, after that you can use hide. Thank you.
Yeah, fine. Thank you. Okay, and then it comes to placement and routing engineer, routing and verification. Here, the physical design engineer role comes into picture, and in that physical design also, like for placement, routing and verification, there will be multiple levels of engineers will be involved. Like the person who places exactly like different components what we have may not be good at how that clocks will be distributed. Like we know the concept of clock tree synthesis and all, like that, based on how it should place and to reduce the routing congestion actually. Like that, there were many strategies and many features we need to include. So placement and routing is not only one engineer. Here also there will be multiple engineers involved. Like at each stage, I can roughly say around 10 engineers in vertical actually. And then physical verification and tape out engineer. This is generally the testing comes into picture where I work actually. Whatever the design we are done so far, if it works properly, then only we can release to the market. So to release that to the market, we have to test that. Okay, once we tested, if the design is better, we feel, then only we'll send it for manufacturing. After manufacturing also, post fabrication testing, like see, when you test it on the software, it will be good, like a simple AND gate. If I'm designing, all the inputs are proper, output is proper, but when you fabricate it, if any input is shorted with any pad or in or both the inputs are short circuited, like that, if any real time problems comes into picture, those are called post fabrication testing and validation engineers. Okay, so in this complete process, there will be around 20 to 30 engineers involved in the entire process actually. And what are the generally used tools? As the industry leads with the three tools like mental graphics, cadence, and synopsis. These are the three major tools we use in VLSI industry. And of course, at different levels, it has different packages. Like Xilinx is now opted by AMD, and rest all is three only: cadence, synopsis, and mental graphics. These are the tools. And today, as related to our topic, contemporary techniques, or what are the latest technologies we are using in VLSI industry. Actually, here these are the different agenda. I'll go one by one in depth actually. Emerging device architectures. We know so far we have CMOS FETs generally used actually in the latest things. But where those can be replaced by GAA FET, like where the current generation will be very high when compared to MOSFETs. And tunnel FETs and graphene material. Graphene will replace like silicon and germanium, whatever the materials we have, it will be replaced by this graphene, where the results, like whatever the parameters we have, like a current generation, leakage current reduction, subthreshold current reduction, those parameters will be bettered, like improved, we can say simply. Either it may be increment or decrement, whatever it is improved in this tunnel FETs or graphene technology or GAA FETs. So instead of using traditional MOSFETs, we can use these. So nowadays the work is going on this GAA FETs and this tunnel FETs in graphene technology. Okay, if anyone chooses to research on this, they can choose this as one of the best topic I can suggest. Next, advanced processes, nodes, and packaging. Here, as we know, the scaling is very much shrinking nowadays. We are going with 2 nanometer and 3 nanometer technologies, where the density is very, very high actually. The market release might be 7 nanometer, but the work is going on in 5 nanometer and 3 nanometer technologies nowadays. The shrinking of the device, like previously, as we know, the mobile size was almost half of the size of a laptop, a small laptop. But nowadays there were many features, and mobile is very narrow and thin in size. Okay, like that is due to the scaling of the size and its scaling of the different channel widths of the transistor. And when we go with packaging, here we have two methods to package actually, that is 2.5D ICs and 3D ICs. Generally, we know 3D IC is stacking like vertically one by one. We integrate together and we design that. 2.5D ICs are nothing but these are horizontally placed actually, here like this. 3D ICs, so die by die, those are vertically placed, and these are connected through SVs. But whereas 2.5D ICs, dies are placed horizontally and connected through silicon interposers. The thing is, here size required is more actually, 2.5D ICs, but at the same time complexity is less. Here 3D ICs occupies very less area, but complexity is very much high, like temperature might increase drastically compared to 2.5D, because area here we are using is more. Here it is less. Like that, there are pros and cons in 2.5D ICs and 3D ICs, of course. And nowadays generally used is chiplets, like a combination of 2.5D and 3D ICs. Depending on the structure and its required density, we can use any one of these. Like memory is generally 3D ICs, like vertically they use. Depending on them, like nowadays SoC architectures, we have multiple chips or uh, embedded on the same design, like on the one PCB, and they are connected internally. But that internal chip, whatever we have, generally we call it as IP, intellectual property. That IP might be 3D IC or 2.5D IC. That combination is an SoC, simply like a chiplet kind of thing. And as we know nowadays AI is ruling the industry, as we know. And this VLSI is also introducing AI into this, like some foundation models, circuit foundation models, so like pre-trained AI models, like we know ChatGPT and all, right? When it comes to VLSI, Synopsys is the company, as I said. They have introduced some ADKs actually, like some applications where those are pre-trained, and whatever the task you give, like some prompt you give, it will suggest you in certain way, so that your work efficiency increases with less time actually. As we know, it is like a general kind of application. However, we have in general, but it isn't VLSI field. Next, that means you can what I mean is you can concentrate how you can introduce AIML into VLSI applications. There also we can concentrate. And next one is heterogeneous integration and sustainability. As I told previously, chiplet based architecture. Chiplet based architecture means multiple chips will be integrated onto the single SoC, where which will have different features, like multiple threshold voltages. That means different power application, power needs it will have, different temperature needs it will have, but we are integrating all together, uh, and we are making this circuit sustainable. So what are the techniques we are using? Like for example, if we have threshold voltage of 5-volt circuit and a threshold voltage of 7-volt circuit in general, but of course nowadays low power circuits we are using 1.5 volts and 2 volts, like that. 5 volts and 12 volts means the threshold voltage is completely different. But I'm designing that those two circuits on a single board. So those two will have different requirements, and temperature for 12 volts will be obviously more than 5 volts. But how this 5-volt circuit will withstand with the temperatures and power consumptions generated by 12-volt circuit? How to optimize the requirements of those circuits and how to design them? That is a kind of thing we look into this chiplet based architectures. Actually, there were multiple features. I'm explaining a few features to make you understand actually. And nowadays we
Sorry,
have the
madam.
importance.
Madam, sorry
Yeah.
for interrupt. So I think your speaker maybe getting resound as well.
Actually, sorry to say, there is a puja
Yeah,
going on.
yeah, okay. No
Um,
problem, madam.
maybe that might be giving you
I think
little
I think
resound.
I think it is
Okay.
audible nice only. No issue for that.
Okay.
For me, to me it's okay.
Okay. Thank you.
Is that clear now?
Yeah,
Yes,
yes, ma'am.
madam.
Yes, ma'am. It's clear only. No interrupt.
Okay. And eco chip studies. We have nowadays, like we are going with EV vehicles, like environment friendly. The same concept adopted here. Eco chips are nothing but which are environment friendly, which will go with less carbon emissions. Those kind of chips we are supposed to design actually. So people are concentrating, like Intel, AMD, whatever we have nowadays, whatever the chips generated are compulsory, those should be eco-friendly actually. Eco chips they are generating. Now almost it is mandatory for every company actually. So they can concentrate on these eco friendly chips, how to manufacture, and what are the different parameters they have to consider to reduce the carbon emissions. This is one of the best area I can suggest, because which has more life compared to the previous. Next one is power approximate security trends. Of course, VLSI trend started with low power, I can say. After the size, the people more people concentrated on power reduction actually. So for most of the work is done in low power VLSI applications, we can say, of course, and it continues. Scaling is almost, it is down to 2 nanometer and 3 nanometer. So now it is very much challenging. We can say that a reduction in the power, reducing the size of the device. So only scaling is not only the way. Previously, whatever we have done, we are going to scale down the device so that power consumption is got reduced. So far, whatever the work done is, like previously it is started with 145 nanometer technology, 120 nanometer technology, 90, 45 nanometers. Now the work is going on in 2 nanometer, 3 nanometer and 5 nanometer technology. So there is no much scope for scaling down actually to reduce the power. So what are the other parameters we need to consider to reduce the power consumption? If we concentrate there, that is a good thing to concentrate or do research on that actually. And here one suggestion which is already developed is approximate computing. Approximate computing, as the name indicates, it will not give you the exact results. Then you might get a doubt like, if there are no exact results, how can we accept a design? But there are certain fields like multimedia. The better example I can give you is pixels, like a camera. When you design a camera, uh, we have some pixel size, right? For example, the screen size, generally when we watch a 760 by 1080 pixels, like that we'll use, right? Instead of 1080, if it is 1075, is there any difference can be found? No, right? There is no much difference, and there is no much difference in the quality also. Like if we introduce the same approximate computing in space technology, it will never work. We accept. But when it comes to simple pictures, instead of 1080, if it is 1075, it is acceptable. Even though you are generating a good picture without much resources. Those kind of areas we have where approximate computing also has very much importance actually. That's why here in the multimedia is one area actually. There we can concentrate. Like see, whenever I can give you one more example. If I go for addition, like what 1000 plus 50 is 1050. It will give you the answer in 200 nanoseconds. Instead of that, 1000 plus 50 is 149, where the application is also more important. You should concentrate on the application also. Instead of 1080 nano pixels, it is giving 1079 as the addition, but instead of 200 nanoseconds, it is taking only 50 nanoseconds. So there is a difference of 150 nanoseconds of propagation delay. So now tell me whether we look at the 1 pixel difference or 150 nanoseconds of time reduction. Definitely we'll concentrate on 150 nanoseconds of time reduction, right? So that kind of applications we use in this approximate computing. And this is also one area where we can concentrate. What are those approximate computing areas we can apply, and what are the applications in that we should go with. And security systems we have. And next, ultra low power techniques like frequency scaling. Hello? Hello? Any doubt?
Madam, you can continue. Someone unmuted.
Okay. Okay. Okay, as we discussed previously, low power techniques. Here, power or clock gating techniques we have, and power aware verification. that means depending on the power, different power levels if we need. Like one circuit needs some X power, other circuit needs some 2X power, like that. Depending on the power requirements, we divide the circuits and we connect them accordingly actually. And I'll come back to this power aware verification where actually I'm working. I'll come back to this in detail. Okay, and next, this one we already discussed. Beyond CMOS, we have like tunnel FETs, GAA FETs, spin-based logic, and graphene transistors. Instead of silicon transistors, we can concentrate on graphene transistors, where with the same input we can get multiple output parameters improved actually. Okay, this is whatever we discussed, what are the different areas and where we can concentrate. Whatever we discussed so far, this is the summary. Devices and nodes, we can concentrate on GAA FETs and nanometer technology. And instead of CMOS, we can go for other alternatives like graphene materials and this. I'm just summarizing the things. Packaging and integration. Here chiplets we can use instead of regular packaging methods. We can use these chiplets where it integrates 2.5D, 3D and all the kinds of chips in one architecture. And AI models, of course, AI can be introduced in everywhere to automate the system. And next, sustainability, like eco-friendly designs we need to go, how to design a circuit which is eco-friendly, and this approximate computing and hardware security systems. Okay, these are the different areas in VLSI we can concentrate in outer line actually. Here when we go in depth of this, again there were many things where we can concentrate. Okay, and now I'll in these actually I have my area which is related to low power things actually, that is which is testable circuit. My exact area is designed for testability, like how if you have one design, see I say that I have designed an AND gate, for example. What is the property of AND gate? If any one of the input is 0, output must be 0. So I say that I designed an AND gate. It is good, I say, but it should be verified, the structure, like whether it is giving the required output or not. For one input is 0, it should give output as 0. If all the inputs are 1s, output is 1. If it is simple AND gate, we can say we'll give the simply 4 combinations like 0 0 0 1 1 0 1 1 combination will give, and we'll verify the output. But nowadays like DDRs is containing millions of transistors, one single chip actually. So for each and every transistor, I can't go inside and give input. And if it is a single chip also, we can't test every part of the circuit, right? Whether it is giving proper output or not at every stage. Simply like when you have written a simple Verilog code is okay. Like and of A comma B, output is C, something will write in Verilog, right? And of course, if I give stimulus, I have written a test bench and it is tested. For 4 combinations I have given. Here, till the development stage, it is okay. But when it comes to fabrication, but post fabrication and pre-fabrication also I have to test, right? So at any stage of the design, I should be able to test that particular circuit, whatever I have. That means if it is a simple AND gate, I should be in a position to test A leg, B leg, both the inputs and output Y at each and every stage, whether those are working properly or not. So converting that particular circuit, whatever we have, into testable circuit. That means whatever is the stage of the circuit, I can test each and every point of the circuit. Yeah, I'll just a minute. I'll go back to that. Yeah. Here, for example, if I have this particular AND gate, here this is A, this is B, and this is Y output. As I said, 0, 0, 0, 1, 1, 0, and 1, 1. These are the 4 combinations I have, so that it will give you like a 0 for first 3 cases and 1 for this case as the output. Okay, this input is called as stimuli or stimulus, we call it as. That means all the possible inputs. All the possible input combinations. This is called as stimuli. But see, if I have 2 inputs, here how many combinations? 2 power 2 is 4 combinations. If I have like 10 inputs, 2 power 10, that is 1024 combinations I have to test, which takes lots of time. But as we discussed, there are millions of gates, means 2 power 100, for example, which I can't imagine. It will take some years of time to test the circuit. So here it is not possible to give all the stimuli. That means possible circuit, possible combinations. So instead of stimuli, here I'll go for test vectors. See, there is a difference. Stimuli is different, test vectors are different. Stimuli is all the possible input combinations. Test vectors are the input combinations which can detect the fault. Combinations which can detect the faults. See, for example, here among these 4, for certain fault, I might need only these 2 combinations or these 2 combinations. So if I need, for example, only these 2 combinations, it is wasting of time giving these 2 combinations, right? But how to know which combinations only I have to give? That's where that DEFT or design for test comes into picture. Design for test engineer comes into picture. Like what are the input combinations I have to consider for a particular test, actually. Okay. Now I'll come back to this one only. Before going to that, I'll give you some.
Hello.
Yes.
Madam, good evening.
Yes, sir. Good evening.
Madam, what you told DFT engineer will do, then that verification engineer also do the same thing, no?
There is a difference, actually. Verification engineer will do like whether the circuit is working properly or not. Let me show you. I'll come to your point. See, I have a flop here, D flop. 3 flops I have. Okay. I have a simple flop connected. This is primary input and this is primary output. Okay, simple RTL design engineer will write code for that. Verilog D flip-flop will write, and 3 times it will be instantiated, and this is input, this is output. Okay, that is design engineer. When it comes to verification engineer, the thing is, for example, if I give a 0 here, because all these are delay flops, here I should get 0 only. Like after 3 clock cycles, if it is a serial shift, right? Here 1 clock, 2, and 3rd. After 3rd clock pulse, I should get this 0 here. If it is 1, I should get 1. If this is okay, that is called verification. And one more thing also, verification engineer should cover fault coverage. Generally, this language will be used. That is, whatever the digital code, system design code, whatever is given. Hello, am I audible?
Yes, madam.
Yes, ma'am. Some
Okay.
back voice is arising, but okay.
Yeah, it's puja is going and I can't do
Yes, ma'am.
anything for that.
It's
Used
okay.
everything. Okay. Okay, it should cover all these flops individually. Like we should be able to reach like from here to here, whether it is reaching properly or not. From here to here, reaching it properly or not. From here to here, it is reaching properly or not. Some like assertion kind of things they will use, and they will test. But when it comes to DFT engineer, that is different scenario. Not the same circuit we test actually. Verification engineer will not change the circuit, only testability they will increase. But DFT engineer will add some circuitry to this. See, for example, this is primary input, I can easily test, like whether it is proper or not. This is primary output, I can easily test. But if I want to test this area, I can't go inside, right? So what this DFT engineer will do, design for testability. That means converts this design into testable circuit. So they will add some circuitry. Here I'll take some multiplexer will be added. This input is given here. Some external test signal here. Some test signal. I'll come to in detailed point on this. So this particular point can be tested through this multiplexer, and here this will be connected here. So this will be divided and connected through a multiplexer so that here output can be tested. Here this input also can be tested. And here also.
One small doubt, ma'am. If you add this kind of circuit into it, the area will be increased, ma'am.
Yes, area will be increased definitely. But see, I have a circuit which has some, for example, some 10 million transistors. After designing, when it goes to manufacturing, if there is a defect on this particular flop, right? But I don't know that at this particular flop I have the defect. But at this particular area, at this output, I'm getting some error. Instead of 0, I'm getting 1, or instead of 1, I'm getting 0. But I don't know that whether this flop is causing the problem, this flop is causing the problem, or this flop is causing the problem. Because in this complete series, I have to test each and every flop, right? Yes or no? So to avoid that problem, we are making each and every flop testable. Now actually we have simple test where it will give you directly this particular some if I say XYZ names, Z flop is causing this particular error. Tool will give you direct this flop, so that I'll directly go to this flop and I'll correct what is the problem. I'll check what is the problem and I'll correct it. But that is possible only through if I introduce these multiplexers and if I test each and every flop. That is called, generally it is called as scan insertion actually. This is one step in DFT. Okay, hope I answered your question. Any doubt?
Madam, one more doubt, madam.
Yeah.
Yeah, well, suppose we are designing a 4-bit shift register, then we have 4 flip-flops now. So in actual shift
here
register,
one more will be there.
Yes. So then actually we have in our IC only 4 flip-flops. Yes, while
Okay.
testing, while DFT engineering testing, that this multiplexer and everything, extra circuitry is there, no? So
Yes,
is
yes,
that
definitely.
available in the shift register circuit, or it is separately on other board?
No, shift registers we don't consider because simply it is shifting the data only, right? We
Yes.
shift registers are excluded actually. We have some rules actually while adding to which circuits we need to add, because shift register functionality and this data transfer functionality is same, right?
Okay.
So this addition of multiplexers to shift registers will be excluded. If you have some combinational circuitry here, if this kind of circuits like that, like some extra circuitry, if you have, in that cases generally we add shift registers are excluded actually, because there is no other circuitry in between these two registers, right? There were some rules actually. Yeah, good
Okay,
question it is.
madam. Actually,
Suppose
what exactly M-based memory built-in self-test?
ma'am, actually, SIP register is excluded now. What's the necessary for using
Yes.
this kind of additional circuit? That is not possible.
See, in a circuit there is it is not only built up of shift registers, right? There will be some there were many more circuits. Among some hundreds of circuits, I'm excluding only shift registers. Other 99 I have, right, which can cause problems. So there this concept comes into picture. Yeah, I'll come back to this M-based because it is a start
register,
point only.
Sorry for the
Yeah.
interrupt, ma'am. SIP
Yeah,
register,
no problem.
SIP register consists of some flip-flops. Yes. Now I
Yes.
think you might be taken 3-bit or 4-bit. Based on that, we can
Yes.
also connect that flip-flop, number of flip-flops. So
Yes.
if the flops is there, then only we can do these kind of tests. Suppose it will be excluded in your design, what's the necessary for connecting this additional circuit into it?
See, do we have any circuit which has only combinational part?
No. But
So there will be compulsory sequential part. Without sequential part, we can't store the bits and we can't do anything, right? If you have
really.
sequential part means definitely there will be some flip-flops. So before the flip-flop only, we are adding this multiplexer. We are converting that flop into testable or scannable flop, we are calling it as. Pure combinational, we don't convert.
Okay. Good.
Okay. M-Best will discuss later because it is a little early to discuss before knowing a few more concepts actually.
Okay, we got it, ma'am. Proceed.
Yeah, okay. Yeah. I'll come to DFT now. I think like what is the need for DFT? It is clear to everyone. Like for combinational circuits, only pure combinational, we don't insert this DFT concept as he asked. And shift registers also, because shift register functionality is to simply transferring the logic. In that case also we don't need, but there are many more functionalities apart from these. There we include this DFT actually, that is converting the normal circuit into testable circuit. Like at any point of time we should be able to test the circuit, so we convert that circuit into testable circuit. See, when as he asked, if it is 4-bit flop, when if you think in that way, it is adding 4 multiplexers, so area increases and all. In that point of view, it might you might be thinking like more hardware is included. But when we think in the point of view, like millions of transistors were there in the circuit. For example, see 100 flops were there in a single chain from input to output. 100 flops were there. At the output, I have an error. So I don't know which flop among the 100 is giving the error. Sometimes it might be 1,000. Like millions of flops, I said, right? Millions of flops means it is when it comes to flip-flops, it is around scan cell count, we generally say 2 lakhs, 3 lakhs, where we work on. Among those flops, which flop is giving you error, it is detecting it is impossible actually. So when you introduce this DFT concept, directly it will give you so and so flop is causing the error in so and so line, like that it will give you. Otherwise, there is no flexibility of giving that flop name actually. So we have to test all the 2 million flops, each and every flop, which one is causing the error. Where it makes a sense actually. DFT makes sense here. And here generally we use the two terms which are very important, controllability and observability. As the name indicates, controllability means where you should be able to give the inputs. That AND gate, simple AND gate only we'll discuss. A and B inputs I have, right? A should be either 0 or 1. B also should be 0 or 1. If I'm able to control those two inputs to change it to 0 and 1, I can say that those inputs are controllable. And output Y, if I'm able to observe, depending on the inputs, output is either 0 or 1. I can see both the outputs. Then I can say that I'm able to observe the output. If whatever is the case, output is only 0, then there is no 1. That means it is not proper. Or if it is only 1, no, I'm not getting 0 for any combination. That means there is some error in the circuit. Like that, for each and every input and output, you should be in a position to control the inputs and observe the outputs. So in that way, we change entire circuit into controllable and observable. That circuit is called as testable circuit, designed for testable circuit. And see here, size increases, of course, because we are adding some multiplexers or some test points, we can say. It increases the area, but here you can see reduces the cost of the test. Design cost, it might increase, but see, after manufacturing some hundreds of chips, if the design is not working properly, the best example I can give you, in mobiles also, when it comes to iPhone, some 13 or 14 model is not working properly when compared to 15 and all. That means they could not find that bug in the initial stages. Not only that thing, any digital circuit. If it at the initial stage, if we are unable to find that bug, means at the end process, like end design, it will reflect actually. That means quality we should compromise. And everyone knows one structure in OnePlus, there is a blue or green line we are finding. That is a bug actually. That means at early stages they are unable to find it. Because of that, there will be some, of course, there is some quality issues on OnePlus, and obviously it will reflect on the sales. And one car company, I didn't remember properly, they called all that release to they called it back. There were some issues in that, battery problem or something, I forgot the name actually. Like that, if at early stages, if we are unable to find that bug, means it wastes lot of cost after manufacturing. Means here it is before fabrication, we can say. Before fabrication, we test the circuit. Pre-silicon, we call it as actually. Before fabrication or pre-silicon test, we do in DFT, We convert the entire circuit into testable circuit. We test at each and every point of the circuit, whether it is controllable at the input and observable at the output. Then only it will be sent to manufacturing. This is all we discussed. Yeah, this one also we discussed, controllability, observability.
Ma'am, good evening, ma'am.
Yeah. Yes. Yeah, tell me.
Just now you said that it has raised some bugs in I13 or I14. That bug has been resolved coming to the I15.
Yes.
Yes. Means when coming to this DFT, when DFT has tested that I14, and they resolved that the bug has, and that the bug is resolved coming to the I15.
Yes. That means pre-silicon, they didn't able to detect that bug, so that it has come in the fabrication. So when they came for the next release, they found that bug, they resolved and given the next release, actually solving that problem.
Series they have released it. Means after resolving that bug in the which series we are using, and the next coming series won't be there, ma'am.
It won't be there, definitely.
Means
yeah, it should be.
Should max.
There might be some other problem. See, sometimes the same problem might be there because of some other issue, might be, but generally 99% there won't be that issue which has once.
Means you are saying that all this happens only with the DFT engineer.
No, not only with the DFT engineer, test engineers. Yeah, of course we can say, because what are the possible defects we can see, they have to come back with the possibilities, and accordingly they should change the design. See, it is a cycle process actually. RTL designer might be given some X netlist, or
Yes.
given today. Once it goes to physical design engineer, it might change, and the DFT engineer, it will come back and it will change multiple times actually. And sometimes there will be some trade-offs, like if power and temperature compromise between those two, means it is not possible. So few compromises will be there, not reaching every parameter actually. So which one is important to that particular design? So other parameters, they will compromise.
Okay.
Yeah.
Okay, ma'am. Thank you, ma'am.
Yeah. Okay, these are some basic terminology we use: defect, fault, which failure, error, controllability, observability we discussed. Here, this is DFT flow. One is the scan insertion, which I explained you, like one multiplexer is inserted so that the flop will be converted into scannable flop actually. That is scan insertion step. Second one is scan compression. Scan compression is nothing but here it is to reduce the memory size actually. Memory in the sense, not the circuit memory. See, you know better the concept of multiplexing. For example, if I have 4 inputs, instead of using a 4x1 multiplexer, we design that 4x1 multiplexer using 2x1 multiplexers, right? 3 2x1 multiplexers. Why it is efficient means, see, if I have a 4x1 multiplexer, this is 4x1 multiplexer. Instead of this, generally we prefer 2x1 multiplexers actually, where the same circuit functionality. Right here, 2 power 4 combinations. That means 16 input combinations I need here. Whereas here, this is 2 power 2 and this is 2 power 2. 4 plus 4, 8 combinations only I need. So half of the work I'm reducing, half of the time I'm reducing, half of the power I'm reducing, power consumption I'm reducing, everything like that. So compression is nothing but instead of using four flops, we can say in parallel, we are dividing them into 2 and 2, like compressing into 2 and 2, like this way. Better example is multiplexer, I can say. So that the instead of 16-bit memory, here I need to store this, I need 16-bit memory, right, outputs to test, but here I need only 8-bit memory. This is called as test data volume, we call it as actually. That is result of this test data, like for 16 combinations, what is the output? I am storing it in a memory. Here for 16 combinations, only 8 I'll get 8 input combinations only I need. I'll note them in the output. So here the memory requirement, that means test data volume is less here, more here. That means memory required is less here. Half of the memory is required here, right? So generally we prefer compression in that. That is compression step. Next one is synthesis. As we know, like to generate gate level netlist, we go for synthesis. ATPG. This is one of the important step where we are generating the patterns. What I explained for AND gate, where it is. Okay, as I told, the difference between stimuli and test vectors, right? Stimuli is all the 4 combinations 0, 0, 0, 1, 1, 0, and 1, 1. This is stimuli. And test vectors are different actually from these which are needed. Those are called test vectors, and generation of these test vectors depending on different parameters. See, if you have more number of patterns, means obviously it will take more time to test the circuit, and it occupies more memory to store the results, and it more power consumption. Everything required is more actually. Obviously cost increases. So how to generate the efficient patterns? That's where ATPG comes into picture. ATPG, that is automatic test pattern generation. And then after that, the whatever the selected input patterns, whether those are testing properly the circuit or not, that is verified in simulation. Again we verify actually. Okay, here I'll give you 1 or 2 circuits, how the test vectors, how to differentiate stimuli and test vectors. See, for example, if it is defect-free circuit, these are the inputs and 0, 0, 0, 1. This is the truth table or expected outputs. For these inputs, these are the expected results if it is defect-free AND gate. If it is defect-free. For example, if I have a defect, this is stuck at 0. That means input is this particular input A is stuck to 0. That means here I can, if I apply either 0 or 1, it will take only 0. So what are the possible combinations I can give at the input? This is 0. B can be either 0 or 1. That means only 2 possibilities only I can see. And see, because this it is stuck to 0, output is always 0. Because as per the AND gate properties, if one of the input is 0 means output is 0, right? Now I have to always I'm getting 0 means I can sense there is something wrong with the circuit. There is an error in the circuit. I'm unable to make it to 1. So when I test, if I give 0, 0, output 0, it is of no use that 0, 0 I'm giving, because anyway, if I give 0, 0, 0, 1, 1, 0, anyway, it will give me 0 output. So what is the better way to test? I have to choose a combination where it can generate 1, right? Because I'm unable to get 1. Anyway, I'm getting 0. If I'm giving 0, 0, I'm getting 0. Whether it is the right output or erroneous output, I don't know. I have to give input combinations such that opposite of this value, 0 opposite is 1. Combinations where I can get 1. What are the combinations? 1 and 1. If I give both the ones, I have to check output. It is giving still 0. That means there is a problem with the circuit. I can conclude directly without testing other 3 input combinations. So now I can say that what are the test vectors for this stuck at 0 at A input? 1, 1 is the only one combination. See, stimuli is 4 combinations, whereas test vector is only 1 combination. That means by giving this 1, 1 input, I can conclude that I'm unable to get 1 as output. Some input is stuck to 0. I can directly conclude that. That is the difference between stimuli and test vectors. See, that means the time is reduced by 3 times, right? See here, if I need 4 nanoseconds to conclude, here I am concluding in 1 nanosecond only, giving only one test input combination. And this is if at the input. Of course, say the same at if at output also will give the same. If I have more circuit like
Hello.
Yes.
Madam, how to resolve stuck at open fault, madam? Can you explain that?
Stuck at
Open.
Stuck at open depends on technology. Stuck at it is generally CMOS circuits we find actually. See, if it is open here, if this is CMOS technology, this open, if this is open, output behaves like either 0 or 1. If it is this bipolar technology, it depend output either 0 or 1. That depends on technology and some threshold voltages what we are using actually. Some completely I can say that technology dependent it is. We can't conclude directly. If it is ECL logic, it is different. Intercoupled logic like that. What are the threshold voltages these transistors are working on? Based on that, these outputs will be decided. Like sourcing and sinking currents, we need to calculate. There were many things actually. Directly, we can't conclude that.
Okay.
To my knowledge. Okay, there might be some updates or like that because I don't work on analog circuits. But to my knowledge, that is a thing we need to do actually.
Yeah, actually, my question is how to resolve the stuck at open fault. Okay, madam, it's
Yeah, stuck at open resolving is nothing but, see here, for example, this is CMOS circuit. CMOS circuit, this is inverter, right? PMOS. Okay. This is X, this is X bar. If this is open, this whatever you have completely discharged, right? There is nothing power, like sourcing is not there, only sinking power. That means output is always connected to ground, so 0 will get irrespective of the input, whether it is 0 or 1, right? That means always you are getting 0 means with this we can understand actually. That is the one way. If this is open here means this power will be here, output always 1. Based on that we come to conclusion actually. And
okay.
beyond this if any methods and methodologies means I'm not much aware on this because mine is completely digital testing. I'll go in that.
Okay. Okay, madam. In case of AND gate, stuck at zero
Yeah.
fault, you are generating one test vector for if stuck at 0, then the output is for testing 1, you are generating the test vector 1 1. No? So like that,
Yes.
how to generate test vector for the open circuit that is stuck at open fault. That is the matter.
Yeah, that's what. There will be some methods, but which I'm not much aware of these analog circuits actually.
Okay, man.
I go with the digital circuits.
Yeah.
Only that like outside knowledge I had here.
Okay.
Okay. And
Thank you.
here in DFT generally we use a terminology called a D algorithm, where test vectors can be generated. For example, this is OR gate, and the 3 inputs I have A, B, C, and Y output. And this, for example, if I have some fault, this is stuck at 1 fault if I have. Here 3 combinations, 3 inputs means stimuli is all the, 8 combinations, 000 to 111, all the combinations we have. But to detect this particular fault, here first we have to set this stuck at 1 fault means we have to make this circuit, what are the combinations we have to take it into 0. First make it to 0 here. What are the combinations which gives you 0? Here 3 possibilities, 0 0 0 1 1 0. Okay, and this should be propagated to output. See if you're stopping this, because if this is OR gate, because this is OR gate, if my input is 1, if I give, will this fault reach the output? No, right? Because 1 will dominate this input. If for OR gate, if one input is 1, output definitely 1. So always we should make sure that this input should be propagated to output. That means we should make this to 0 compulsory, so that this will be transferred to output. This input is 0. These are the test vectors now. C must be 0 and A, B, these are the combinations. That means 0 0 0 1 0 1 0 0. Here A, B, 3 combinations we can take, and for C it must be 0 only, no 1. So these 3 combinations only can detect this particular fault stuck at 1 here. Instead of applying all these, only these 3 input combinations, which we call it as test vectors, can detect the fault. Like that, anywhere in the circuit, wherever you have, like at the output or at this input, wherever it is, if it is stuck to 1, make it 0, what are the possible combinations? If it is stuck at 0, make it 1, what are the possible combinations? That means we should try to set to the opposite value. If you are unable to, means only those combinations will detect the fault. Hope it is clear how test vectors are generated generally. Okay. Now I'll come back to my things. Okay. That is ATPG part. Simulation means again verification with time, actually, whether we are able to match the timing constraints or not. Okay, this one all I discussed. Like a simple flop is converted into scannable flop. Test mode, it is something else, which I discussed everything actually. In between, if you want to test how the circuit is converted. Okay. Yeah, as someone raised, there is a area overhead disadvantages. Power consumption increases as multiple circuitries inserted, but it makes the test coverage and test circuit efficiency increases. Quality of the circuit will be improved when you make that circuit testable, actually. And here, how can we convert that non-testable circuit into testable circuit? There are multiple methods, but multiplexer based scan cell method we use. Like normal, this normal flop is converted into scannable flop, including this multiplexer. Like see, if scan enable is equal to 0, it will select this D input. That means regular functionality it will go. If scan enable is equal to 1, scan input, that is test mode. We are testing whether this input of D is properly propagating to next D of the input. Like that, if you have multiple chains, that means all the flops are proper or not. We are testing. That is test mode actually. We are converting that. There are other two scan cells also, but generally we don't use them, clocked scan cells and LSSD, which occupies more area. So generally we don't use them, only first type we use. So I'm not discussing these two. And here different scan types like full scan, partial scan and partition scan. Full scan is nothing but each and every cell. See here, each and every cell is converted into scannable flop, like multiplexer added to that. That is full scan. And a partial scan means some part of the circuit. See here, these flops are not converted. These flops are converted into scannable flop. That means as someone raised, if these flops are part of shift register, no need to convert. Like that, there were some rules like which flops are need to be converted, which flops are not to convert. Like it is of wasting area, adding extra circuitry. In that case, we don't add this scannable flops. That is partial scan. And the third one is a partition scan, which we use generally. Partition scan is nothing but like if you have an SOC has multiple IPs. So IP level, each and every circuit we scan insert differently. If you have like a circuit, inside that B, C, D I have. So scan insertion is done at B level and then integrated at A level actually. Like internally sub components are scan inserted individually, and all those together scan stitched at the system level actually. That is generally used. Why it is a preferred means, see, if I have see, for example, in this circuit, this is A circuit. Internally, I have B, I have C, and I have D. This generally we call it a subsystem. This is SOC level, the language we use. We also call it as IP, intellectual property. Here, see, the best example I can give is mobiles only. See, for example, this is camera feature. This is number of processors. This is some other battery. Okay, these are the three features. Accordingly, some X circuit generated inside. See, for the next release, instead of octa core, they want to go for 16 cores, hexacore. Okay, so do I need to change this B circuit and D circuit? No need to change, right? So B and D will be as it is. So these partitions we don't touch, and C will be completely replaced by some other circuit where octa-core is replaced with 16 cores, hexacore circuit. So these two are untouched, and according to the changes made in C, we reshuffle at the A level actually. So if we don't go partition level, even though we don't need changes in B and D, if we don't do it at a partition level, we need to rescan everything actually. So where it wastes time. That is why generally nowadays, whatever the circuits we have, these are partition level only, I can say. Partition level, each and every circuit, they insert DFT for this circuit, DFT for this circuit, each and every IP level or subsystem level we do it, and we call it as retargeted SOC level. Okay. Okay, to change that circuit into controllable, we add some test points, like to improve the controllability and observability. Here I don't want to concentrate on this. It takes a lot of time. And I want to introduce you one more important field. It is 8:45. Okay, I'll little speed up these things. From this DFT, as I told, pattern generation is the more important scenario here. Depending on how many patterns and what kind of patterns we generate, it will give you the quality of the circuit. Like as I told, instead of stimuli, we are going for test vectors. Among them also, how many it is selecting? Like 3 it is selecting, 1 it is selecting. Based on that, it is one research area. We have adaptive test pattern generation. In this adaptive test pattern generation, as the name indicates, it is adapting the qualities based on previous analysis. Like previous, when I tested previously, what are the different test patterns it has generated? Then what are the kind of issues I'm getting? Based on that, dynamically it will change the patterns. For example, 0001, these two patterns, first 00 I have given, next 01 I have given, for example. Then it has certain data, but it found that first giving 00 is not so intelligent move. Give 01 first, then 00, so that the fault can be detected at early stage. That kind of suggestions it will give you based on the previous data. So this we call it as fault grading actually. That is 0, instead of 00, I have to use 01. Grade this 01 as the first. Fault grading is the technique we use actually. So for that, we have different AI models. For that, we can work on that. And I came back to a narrow down area where test pattern generation, where we can go for research kind of thing actually. Okay. And here, like why it is important. These few things we have discussed already. As I told, instead of multiple test patterns, it will reduce the test pattern count based on the previous analysis. And if you reduce the number of test pattern counts, means test time, test power consumption, everything will reduce. And at the same time, quality of the test will be increased. Will never compromise on the quality of the test. Test quality improves, so that yield automatically improves. And here dynamic test pattern test pattern selection. As I told in the previous case, dynamically it will see, I have applied 10 patterns. Based on the 10 patterns analysis, it will select the 11th pattern. Like that, we have to design a module. It should analysis dynamically, that feedback is given back, so that it will analyze the previous data output, and it will generate the 11th pattern. That means the next pattern. Like that, we have to design the circuit. For that, what are the different parameters we need to consider? You can research on that actually. That is the one good area to work. And real-time limit. Yeah, as here mentioned, local area also matters, right? See, if you have a design which is designed for summer, may not work for in general. I'm saying, of course, whatever these designs will work for any environmental conditions. Like real-time limit means, I'm telling you, like summer means it is around 40 degrees centigrade, winter it is around 25 degrees centigrade, like that. The design which works efficiently at 25 degrees centigrade may not work at 40 degrees centigrade, right? Like that, in real-time environment, based on that, it has to adjust the patterns. Like that also it has to go. Like that, different sensors we need to give, like voltage sensors, temperature sensors and all. We have to introduce them. and based on that it has to generate the patterns. That is another way. And data driven optimization. Okay, see here as it is given, it is a low power circuit or high power circuit. As we discussed earlier, different circuit might be with different threshold voltages. I have a circuit which needs a threshold voltage of, if it is 5 volts means generally threshold voltage is 0.7 volts, right? So if it is 3 volt circuit, threshold voltage accordingly scaled around 0.3 or 0.4 only. But if I give this 0.7 is the threshold voltage for 5 volt circuit, this here output is 0 for me for 5 volt circuit if I give 0.6 volts. But whereas 3 volt circuit, if I give 0.6 volts means it works efficiently. It will give you some output, not zero output, right? So depending on that, what kind of the parameters you are considering, based on that parameters also, it has to adjust the patterns and give you efficient, should give you efficient patterns. Like that, how to design a circuit. Next, machine learning circuits, like some AI automated algorithms, how to introduce into that, and how to generate patterns is AIML introduction, of course. Skipping unnecessary tests, predicting failures beforehand only, like that. And these are the different tools we have at different levels in AIML, which is integrated to VLSI. And skip or retest. That means whether to skip or retest. Like we know that if we know a good student, we will ask only 2-3 questions. Like we are in assumption that yes, that person can know, that student can know. But if it is another student, can we believe 100% no, right? We'll test at multiple levels. In the same way, if it at first level the parts are good, then next level it will skip some patterns. Or at the first level it is showing you there are some faults in the circuits, means it has to be tested with more number of faults. Like that, it should analyze the data. For that, how to model the circuit. Like that, we have to design the circuit accordingly. Next. Okay, this is a summary for that, whatever we discussed based on the previous data at different levels, how to prioritize the patterns, like among the 100 patterns. And one more thing also, if you have 100 patterns, all the 100 test vectors also may not be useful. Among that 100, some 60 also can test a circuit if you given certain order. Actually, that is called pattern prioritization. Okay, like if 0 is testing priorly, if you give 0 1 first, means it is of no use. Give 0 first, the order in that way. Like that, pattern prioritization also important. But how to prioritize that, what are the parameters we need to consider, and how to design the circuit, we should work on that actually. Okay, some examples where all these are used are cloud, NVIDIA, AMD, all these companies, Intel and everything, they are using in the mobiles and this processors also. And what are the benefits and what are the challenges in this? This adaptive test generation reduces test time and cost, but to make it adaptive test pattern, we need to give some extra infrastructure. We have to, like circuitry, as you said, for DFT circuit also there will be some area overhead, right? Here also for adaptive testing there will be some area overhead, and enhances yield and profitability, of course. But what is the risk? If any model is not detecting that particular fault, means again it's a flaw at the end. And of course improves the test quality through ML. but good data collection must be proper in that way. If the data collection is not proper, then we may not reach the requirements. Real-time feedback loops, it should work properly. So if you have any circuit is having feedback, means complexity obviously multiplies by multiple times actually. So complexity increases. Okay, in summary, we can say like it is good to adapt adaptive testing actually. But at the cost of course, everywhere some trade-offs will be there. And there is another test called power aware test. Okay, only 5 minutes left. Fine. Power aware test, it is similar to adaptive testing, where in adaptive testing we are concentrating on test patterns. But whereas that is count of the patterns, we are reducing the number of patterns we are reducing, so that the end result we are making better. But whereas power aware test, in this power aware test model pattern generation, we concentrate purely on power, as the name indicates. We are concentrating on the power generally means, as we know, multiple threshold voltages comes into picture. See, if I need a circuit where more power is needed, and I have an application where it needs very less power, so I can't drive those two circuits with the same power. One is 5 volt circuit, one is 3 volt circuit, one is 1 volt circuit, like that I can't drive this 3 volt, 5 volt and 1 volt circuit with the same input supply, right? So I have to give these three different circuits, I have to generate three different pattern sets actually. And for 1 volt I have to give different pattern set, for the 3 volt I have to give different pattern set, and that order of the patterns also should be like the patterns which needs more power generally will give first, and at the end will give the patterns which needs less power. Generally the patterns, how to know which patterns needs more power and which patterns needs less power? Okay, it is a simple thing where we have multiple transitions from 0 to 1, 1 to 0. It is a general logic which you know. 0 to 1, 1 to 0 transitions are more means it needs more power. If you have less number of transitions means it needs less power in general. Okay, and of course depending on what is the circuit power needed, like whether it is 5 volt circuit, 3 volt circuit or 1 volt circuit, depending on that also it changes. Okay, what are the challenges in this power? Excessive switching, that is transition. If 0 to 1, 1 to 0 transition if you have, then IR drop will be more. Okay, it takes more time, sometimes it may not reach to 0 or 1 within the time. So timing failures comes into picture. If more transitions, heat temperature automatically increases, thermal damages can come into picture. Power domain crossing, as I told, 3, 5, 1 volt means different circuits needs different voltages. See, 5 volt circuit, 0.7 is the threshold voltage. But if you give the same 0.7 volts to 1 volt circuit, the maximum voltage you have given, that means high logic you have given, that means. So depending on the circuit, we should work on actually. We should give that proper patterns to that circuit. For that, how to design the circuit actually. Here, what my point of view is. And of course, leakage power, depending on threshold voltages, leakage power also varies. These are the challenges we have. Based on these different challenges, how you design your circuit, where to concentrate. Like that, we can research on that. Okay, this multi-power domain. Okay, here generally multi-power domain aware circuit, we have unified power format and common power format. That means common power format means all the chips in the design are using 5 volts. That is common power. Unified power format means 5 volt circuit I have, 3 volt I have, 1 volt I have. Accordingly, we have to design. That is UPF models and CPF models we call them. And the scan stitching or this DFT insertion also according to them. 5 volt it is separate, 3 volt it is separate, and 1 volt it is separate. And these are the tools generally we use. Synopsys, DFT Max, Cadence Models, and Siemens Descent are the tools where we use this power aware test models. Power gating. Okay, this one already we discussed. Okay, thermal aware testing. Okay, if the simple logic here actually, the if temperature is more, power consumption is more, obviously temperature increases. So depending on, we can't apply the same thermal sensors for 5 volt and 3 volts. So depending on that, we have to use. So for sensors is the major uh, parts here. Based on that, we have to design the patterns actually, which patterns we need to pass, which patterns we need to be in which order we those to be sequenced. Like see, if it is a 5 volt circuit, if there are multiple transitions means automatically temperature increases, it damages the circuit. So instead of that, you need to select the patterns where transitions are less. If it is 1 volt circuit, if you have more transitions also, no problem. Like it won't generate much temperature. Like that, we have to uh, dynamically change the patterns actually. But accordingly, the circuit should be. Okay, scan chain partitioning. As I told, like depending on which kind of circuitry, we have to reduce the length of the scan chain. Like multiple transitions must be reduced ultimately. Whatever it is, power aware means transitions must be reduced, but at different levels. Like here, time multiplexer segments means I gave you one example. Like instead of using 4x1 multiplexer, we use 3 2x1 multiplexers where that number of inputs are reduced, that is memory is reduced. Here multiplexer segment means it is like parallelization kind of thing, I can say. TDM circuits we have, right? That kind of, instead of using all the scan chains at the same time, some time slots will be given. During that time period, those will be tested so that power consumption reduced and the temperatures gets reduced. And this launch and capture and launch and shift, this is very very important topic actually among all of them. During the capture you are testing, like a launch on capture, that means when you are capturing the output you are testing, or when you are shifting the output you are testing. Actually this is a big topic, I can say. This will give you end result also sometimes. Like launch on shifting, while shifting the data you are testing, while capturing the data means that scan enable pin 0 and 1, and launch and shift needs completely dynamic way of testing. Like instantly it has to change from 0 to 1 according to the circuit's frequency. At the we call it as at speed testing or transition testing. Whatever the circuit frequency, at that frequency the testing speed should be actually. Here it will give you more switching activity and IR drop is more, but less patterns it will give you and accurate results it will give you. But the risk is it should be tested at the circuit frequency. That is a major problem with launch and shift. Launch and capture may not be tested, like no need to test at circuit frequency. Like if it is 4 gigahertz circuit means no need to test at 4 gigahertz. Launch and shift means you should be at that frequency and test. It is little risky actually, but gives you some good results. But LOC, no need of that frequencies, but test pattern count increases actually. And based on the IR drop, patterns has to be generated, like which where IR drop is less, for that it is different patterns, others it is different pattern. Of course ML we can introduce into this power aware test patterns, like machine learning algorithms. we can use, like based on whether it is IR drop, electromagnetic things, and thermal violations. You can consider any of these, and you can introduce certain algorithm into that. This is at a very basic leaf level, we can say. These are all what I'm explaining are. You can choose any of these leaf level points only, and you can work on that so that it can be implemented at SOC level if it works well at leaf level. Voltage scaling. High voltage for high speed circuits, we need high voltage, of course, that is bipolar technology. Low voltage for leakage assessment, that is MOSFET. We came for that only, right? Simply I can say bipolar and CMOS technologies, switching between them, like depending on the type of voltage we need. That is, speed is more, high voltage we needed, blindly we can say. So according to that, DFT has to be developed and patterns has to be selected actually. Concurrent versus staggered based, like how you are testing the circuits. One by one you are testing, or all together you are testing. If you are testing all of them together, means it needs more power and temperature increases drastically. That is staggered, means one by one we are better to test one by one, like that. The kind of TDM it is, we can say. Okay, all these are the tools actually. DFT Max Ultra, vendor is Synopsys, Power Aware, ATPG, Scan Planning. Okay, these are the tools we use. Modus from Cadence, Descent Power Aware ATPG from Siemens, Red Hack from Siemens or ANSYS, VTran from Ridgetop. These are the different tools where we use for Power Aware test pattern generation. And okay, this is the summary of power aware test pattern generation. Like if you have more IR drop or simultaneous switching, we can reduce. Where we can concentrate temperature or multiple threshold voltages if we have, or LOC or LOS based, like based on which parameter you are generating test patterns, like how to prioritize them, how to generate them, how to like feedback and analyze them, so that next pattern we can generate, whether it is in adaptive testing, test pattern generation, or power aware test pattern generation. Almost techniques are same. The point parameter we consider is different. Here we are considering power, whereas in adaptive we are concentrating on a number of patterns. Okay, parameter is different, but like things are like where to concentrate, what is the motto is same. Okay, I'm done from my side. If you have any doubts and all, we can discuss. Yeah.
Yeah, anyone have any doubt, please, you can. Yeah, madam, I have like coming to the scan design rules case. So if the floating inputs are crossed coupled NAND gates or NOR gates, or like a non-scan storage elements are used. So what type of recommendation solutions will be used in case of DFT, madam?
But can you come again? I didn't understand properly. If
Yeah,
floating inputs.
Floating inputs and crossed coupled NAND gates or not NOR gates, or and one more is non-scan storage elements are used in case what is the solutions you will be providing in real time?
Non-scan storage elements, if you have, generally we use a concept called sequential depth actually, like see, I have this is one scan cell, where if I have scan in SI input means scan cell it is. Another scan cell means here when I give one clock pulse, it will reach this output. there is no problem in this case. Both are scannable. Okay, in a single clock pulse, I'll reach to the output. But there will be a problem if I have one non-scan cell here, only D, no scan input. Okay, simply D. Okay. And in this case, what we do is simply if I give one clock pulse, it will reach the output till here, not till here. So this will give you some kind of X value. X masking we call it as. Okay. So here the value is unknown. X will be the value. But in previous case, in one clock pulse only, it is, if it is 0, it will reach 0 here, 1, it will reach 1 here. But in this case, if I have non-scan flop here, this value is X. So we'll give one more clock cycle. This is one clock cycle. And in second clock cycle, this value will reach here. This 0 will reach here. And in second clock pulse, it will reach here. First case, sequential depth is 1, we call it as, and in second case, sequential depth 2 will give. We have some settings in the tool, sequential depth 2. If we have multiple cases in this way, instead of giving this unknown value to the next flop, we'll give extra clock pulse here, so that this value will become known value, either 0 or 1 depending on this previous value. Okay, so sequential depth 2 we are giving. That means simply how many number of non-scan flops you have, that many extra clock pulses we give. And you might be like have a doubt, like if you have like 100 non-scans, will you give 100 clock cycles? No, that should not be the case. Generally, the standard will be 5. They don't allow more than 5 non-scan cells between any 2. Otherwise, we should go for redesigning of the circuit.
Okay. In case of other one is floating inputs case, what you will do?
Floating inputs, for example, if I have this, if it is floating here, there is no problem because it is not disturbing any other circuit. Okay. Because it is not the input for any other circuit, it won't disturb the circuit. This case is okay, but if it is at the input, if it is floating, because it is disturbing this particular input value, it is manipulating, and this cone completely, whatever it is driving circuitry, it will drive. So this is not acceptable. So we should inform the developer to change this input.
Okay.
Yeah.
Yeah, please, anyone is having any doubts?
So thank you, madam. Thank you so much for enlightening us with your valuable lecture on contemporary advances and research directions in VLSI design and technology. The knowledge you imparted has certainly enriched our understanding on various concepts, starting from heterogeneous integrations, eco-friendly chips, low-power techniques, how important is the sequential circuits are, how to detecting manufacturing defects, difference between stimuli and test vector, and all till sequential depth. Thank you so much, ma'am. Before we conclude, is there anyone with a final question? So I would like to thank you again, madam, for your valuable contribution to our faculty development program. I hope the insights which we gained today will definitely inspire us in new approaches at our workplaces like teaching, research, and industries too. So let's end the session with a vote of thanks to our esteemed resource person, Rajita Rani madam. Thank you, madam, and thank you to all the participants. Wish you all a happy Vinayaka Chavithi.
Yeah, thank you, ma'am. Thank you for the opportunity also. Thank you.
Madam,
thank you all.
Madam, thank you very much. Like even though if with the sound environment, you have given a good lecture. Thank you very much, madam.
Yeah, thank you, sir.